Okay, so good morning, everyone. We're going to be looking at the frequency response techniques in our class today. So, this is the first class for the catch up session. Now, today we're going to be looking at the frequency response techniques, and on this, we're going to be specifically focusing on what is the concept behind frequency response, what are its advantages, and what is the difference between your gain adjustment and your frequency adjustment technique. So we'll have a look at this one by one. Now you'll see that the frequency response is on chapter 10 in your Eunomimus Nice textbooks. And let's just have a look at what is the concept uh, of frequency response. That's the first part we want to start on. So here, if you take any kind of a control system, okay, so let's take this as an example here, or for that matter, any kind of control system that we have. They have chosen a viscous damper or a mass spring viscous damper system. It can be any control system. Okay, so if you take this system, right, so let's take this as a control system. We know that this here is our input and this here is your output. Now all this while, when we were discussing about the input and the output, we were basically focusing only on the magnitude. So we were talking only about the magnitude. Now there is a slight challenge here, right? So we talked about the input magnitude and the output magnitude, but nowhere in our discussion did we mention or speak about the phase. Okay, so if you take a simple AC signal like the one that we have for our electricity, it is 240 volts, 50 hertz, right? So all AC devices work or have got both a magnitude component, which is this 240 volts, and they've also got this frequency component. So this here is your magnitude, and then you also have your frequency component. So it is essential that when we talk about the input of a system on the output of a system, we mention both what is happening to the input and what is happening to the output. That is described in this diagram here that you see, right? So let's have a look. So you can see that here they have taken a specific system and they have put it through this is the input. So here you have this one, this is your input, and this input has been applied to a system, right? So you have your system here, and when you apply it to the system you get this output. So you can see here Mi is the input and phi I or theta I, whichever way you want to refer it, phi I is the input angle, right? Now when the system goes through, or when the input goes through this system, okay, it has a different magnitude Mo, and it has a different phase, which is phi I. So when we are looking at any different techniques, we are solely focusing on the magnitude and paying no importance or not looking at the frequency of that system. Now this becomes a challenge because AC signals have got a frequency component as well. So it's extremely important that we analyze and say what is happening to the frequency of the system as well. So that is why we have the concept of frequency response. Right? Now, what are the advantages of using these systems? So let's have a look. Now, one of the main advantages is just what we mentioned here, right? The fact that you're using a frequency response as opposed to you will be able to discuss the phase of the system as opposed to the magnitude only in the different scenarios. On the textbook, you can see that they've specifically listed 4 advantages of this specific approach. So it says here, this technique has distinct advantages in the following situations. So where is the frequency response useful? So firstly, when we are modeling a transfer function from physical data, right? That is, it's shown here in 10.1. That means if you have an oscilloscope output, you can take that oscilloscope output and directly use it for modeling your system, right? That's the first advantage. The second is when you're designing lead compensators to meet steady state error requirements and transient response requirements. Now this is something that we are going to be looking at in our next module, right? So once you've covered that, it will give us a bit more sense. But we discussed previously as well, the main intention of doing control systems is to see what is the transient response, the steady state response, and the stability of a system. And then if there is an issue with your system, we need to compensate the system so that we can fix for these issues. And that is where we look at the concept of compensators. Nextly, another situation is when you want to find the stability of non-linear systems. If you look at all the problems that we did till now in all the chapters, the assumption is that we are talking about linear time invariant systems, right? Now, the advantage of using frequency response, or one case where we can use it, is we can use it to determine the stability of non-linear systems. And finally, it settles some of the ambiguities when it comes to sketching a root locus. And that's the fourth point where we are going to actually go next, where we're going to say what is the difference between a gain adjustment technique and so it is gain adjustment versus your frequency response, right? So here, gain adjustment directly refers to the root locus. Now, the reason why I say that is when we are talking about the root locus in chapter 5, we discussed these various concepts like finding the breakaway and the break-in points. Then we also looked at finding the j omega axis crossing, right? Now all these values, what they do is they actually, if you look here, this concept of k, which is the gain, right? That is why it's called a gain adjustment technique. You're varying the value of gain from 0 to whatever value, and you're monitoring the trajectory or the path that the poles follow when you vary that gain. And you are stating that a system is stable. For example, in this case, in this case you can see that we are finding out where the gain, what happens when you vary the gain and what is the real axis value, such that we're finding out where they meet on the j omega axis. And at that point where they meet on the j omega axis, it is called as the point of maximum stability. Beyond that point, the poles go into the right hand plane and the systems become unstable. So the major advantage of the frequency response technique is that it not only looks at the gain aspect, but also sheds light on the phase of a system, which is critical for most or all of the systems that work on a AC voltage. So this is the difference between a gain adjustment technique and a frequency response technique. Now in the next class we'll look at what are the different kinds of frequency response techniques, and we'll see how we can use those for our frequency response techniques to do the exact same things and maybe a bit more than what we did with the root locks. Alright.